Okay, so let me introduce myself. For those who are year 2, you know me. For those who are year 1, you know me next week. And then, so what the heck is this? This is you, okay? In 30 minutes, impossible. You have very solid understanding of what I'm going to talk. So this 30 minutes, basically just me giving you direction. What are the things you need to look at and practice? That's why I have this picture, okay? Because I just know this yesterday afternoon, so impossible for me to give a comprehensive talk. So you want to start with complete search. So what is complete search? Complete search is not exactly brute force, but if we ignore efficiency, then complete search is brute force. In other words, that means the starting point is brute force. Brute force means search everything one by one. Then, before you do the search, by looking at everything one by one, you need to know what is everything one by one, right? So that means you need the yellow thing. What's the yellow thing? List all possible cases. Okay, list all possible cases is an English sentence for common people. For experts, it's called enumerative combinatorics. What does it mean? Enumerative means you label 1, 2, 3, 4, 5 up to whatever number, all the possible cases. Combinatorics means you count things, okay? And what are enumerative combinatorics? You may know that permutation, the NPR or N permute P, or NCR, N choose R, or whatever thing, you may learn this in your high school, or for those year 2 students, you learned this last year. For year 1, you learn it next week, okay? And basically, enumeration means list all the possible, we don't say cases, we say all possible configurations. These are not the whole story. You also have partition, the arrangement, and this thing. This is the big boss, okay? So again, I'm just telling you the direction you should study, because half hour, come on, you want me to talk about all this and you understand? Impossible. Permutation is this fancy figure. Okay, what is this? This is called symmetric group 4. Okay, don't be frightened by this. It's just fancy name. So you have 1, 2, 3, 4. You also have 2, 3, 4, 1. You also have 4, 1, 2, 3, and you also have 3, 4, 1, 2. What the heck are these? So you can think of this arrow as some transformation. What is transformation? Okay, is this, you have a function called pi. Pi is just, again, a symbol. I can write a chicken, I can write a duck here, doesn't matter. So I have this. What the heck is this? It means I put I in J. So that means what? That means if I have 1, 2, 3, I put 1 to this position, then this means pi 1 is 3. Okay, so this is just a name. Okay, you can think of it as swap in coding. Then what the heck is this? Each of this arrow here is a particular pi. And what about the color? Okay, I have no time. This related to something called symmetry, but basically this figure tells you all the possible way you can arrange 1, 2, 3, 4. So that means you have 1, 2, 3, 4, 2, 3, 4, 1, blah, blah, blah. Okay, then the first question you need to know is how many are they? Because if you don't even know this number, you cannot even do the yellow thing. Yellow thing is you have a set of what? Of all the possible configuration. So it's like you know there's a set and you know all the members in the set. But before you know the set, you also need to know how big is the set. That means how many possible configurations are there. So this is the starting point. Okay, so permutation, combination is not a full story, and because of time, I'm not going to talk about what the heck is permutation. So for year 1 student, I assume you know this. Don't tell me you don't know what is this. Okay, this is 3 times 2 times 1. This factorial means multiply the next number. And the factorial is defined by recursion. And this is, again, a very important mindset. When you write code, try to write something in recursion form. Don't write for loop or while loop. If you can write recursion. And then, so these two, no time. Now, this. So the first thing is called partition. What's partition? These are fancy symbols. Ignore it. Look at this. So I have 1, 2, 3. I have 3 things. And I call it 1, 2, 3. And then, these 5 things are all the possible way you can have a partition. So what is a partition? Well, the name said you split them. So you have to split them. So this split means I have a knife, I cut it like this, then I have this, right? But I also can cut it here, right? Of course, I can also cut like this, right? Nobody said the cut have to be a straight line, right? I can cut it like a curve, right? So again, if I have 1, 2, 3, 4, I can cut like this, right? These two are simple. What about these two? These two are easy. This is what? You cut everything, have 2 cuts. And what is this? Have no cut. So that means, how do you think of how many possible ways you can cut things? It's basically from no cut to maximum number of cuts. Then, if you write that expression precisely, you get something called Bell's number. What the heck is this? It is defined recursively as follows. If you cut at the n plus 1 case, you define it as all the previous Bell number multiplied or scaled up by the corresponding binomial coefficient. So, again, because of time, I assume you know what the heck is this, okay? So I don't have time to explain. So that means if you have nothing, empty set, how many partitions you have? Nothing. Only one way to cut nothing. Nothing. That means 1. If you only have 1 element in a set, how many ways you can cut things? 1 way. That's the set itself. So 1. If you have 2 things, you have 2 partitions. And then so on. This 5 is here, okay? So what is a partition? You have A1, A2, A3, A4. You cut something like what I did. You cut. Okay. Again, let me recap you. You can cut it like this. Okay. You want to make sure they all add up together, give you the original set. G. Okay, I make a mistake. So I call it G. Okay. G stands for ground set. You can think of it as what we are working on, the ground. And then no sharing means all the intersection between whatever AI, AJ is empty set. And non-empty, that means you don't allow cutting nothing. So that means you cut here and nothing. Okay. So this is the first thing. So when you do coding and when you need to do partition, then you need to think about all the point here. Okay. This is called K partition of an N set. N means how many number? So in this case, it's what? This is a partition of a free set. Okay. And then, so I said, I don't talk about P and C. Now I talk about partition. Okay, done. Then next is the arrangement. So what is the arrangement? The arrangement is a special permutation. What is a permutation? Permutation, as I said, pi I is j. So that means if I have this 2, for this particular set, 2 is at position 2. Then if I get this, that means pi 2 give me 1. So that means I put 2 in 1. Okay? Just a technical term. If you consider an array, okay, you know, for those who know pointer, you have the address and the content inside. The content inside can be a chicken, can be a duck, right? Can be anything, right? So now it is interesting that my content inside is also number. So that means it's possible you confuse this 2 with this 2. So better know the name. These things are the content inside. You can call them variable. These things are the location. That means the pointer address in this array. You should call them ordinal, order. So these are order. Order 1, order 2, order 3. These are content inside. And the set of this thing have a number. This is called cardinality, called cardinal. So these 3 things are different things, but these are just fancy names. And then what is the arrangement? The arrangement basically is a special permutation, pi, that you cannot have this. So what does it mean? You cannot, after the pi, your position stay the same. So therefore, if I have a set big P, this means all the possible permutation from a set G, okay, then the arrangement, of course, will be what? Will be a subset. And also it's per subset. That means because you cannot have this, right? So this guy always what? If you have a set D smaller than a subset of other small set, then you can naturally deduce this guy is smaller than P, okay? And what's the formula of counting how many this? It's something that looks like this. What the heck is this? Okay, so for those who know factorial, 3 factorial is 3 times 2 times 1. Now the new thing, I put the factorial symbol in front. This gives you the partition. What's that? Again, this is what? Recursion. So the arrangement at n is what? n minus 1 multiply this funny thing. Then you will ask, what is this value? Well, then you recall this as a recursion again, but subtract 1 until you reach the base case, that is 0 and 1. Okay, this is interesting. You know, 0 factorial is 1. Now, 1 dearrangement is 0. Okay, no time to explain why. And lastly, this is the big boss. For enumerative combinatorics, you need to be very good at this table. And if you are not good at this table, then practice, and practice. So what the heck is this? This is basically almost everything you can think of for combination and permutation. So this is called 12-fold way. What the heck is this? You have 12 possible cases. You have n ball into k box. Think of it as, let's say, 3 ball. So I draw 3 circle. Okay, you have 3 ball. And then you want to put it into k boxes. Let me put it 4 boxes. Okay, let's say 4 boxes. And here is the important thing. I didn't say anything about n and k. N can be larger than k, and n can be smaller than k, and n can be 0, k can be 0. That means this formula works for any k and n that is natural number. Okay? Then you have the following. So first is how you put the ball, and what are the properties of the ball and box. So you have the following thing, because you have 2 class of objects. So this is class 1, this is class 2. So that means you have some property here and some property here. And if you say that this object, their order is important, or I call it distinguishable, that means these are not the same ball. This ball 1, this ball 2, and this ball 3. If I get 1, 2, it's not the same as 2, 1, then this is different from if I get 1, 2 is the same as 2, 1. So for year 2 students, I talked about this last year. 1, 2 is not the same as 2, 1. You can think of it as boxing. Okay, 1 is Mike Tyson, and then 2 is Joe Biden. Okay, and then I go to fight with Mike Tyson first and Joe Biden first is not the same as I go to fight with Joe Biden first and Mike Tyson later, right? Because in the first case, I probably die. In the second case, Joe Biden probably die. So that's different. Again, why I'm talking about this kind of crazy story, crazy example, because this kind of crazy example is crazy. So you have a strong impression in your mind. So whenever you don't know how to think about this thing, make up a crazy example that makes sense, then you will and then remember this crazy example, then you will understand this. Because every time when you want to solve a problem, try to convert your problem into, let's say I fight Mike Tyson and Joe Biden. Okay? So let's say I tell you Mike Tyson, Joe Biden in a boxing round. So now you very likely will know that, okay, they are not the same. So this is what? The order is still important. Order is important, that means permutation. Order is not important, that means what? That means combination. So that means if I have Joe Biden and Mike Tyson equal to this, that means what? You can think of their total fighting power. Let's say they want to fight alien, and then the two fight at the same time. So then in this case, they are the same. But if I fight them one by one, then the order is important. Okay, so what are these things? So you have the following possible case. You have two kinds of things, box and ball. So you either have distinct ball, distinct box, that means different ball are different. You don't treat them the same. Different box are also different. You cannot treat them the same. Or you have one of them distinguishable, one of them not as distinguishable, and then or both of them is just, you can think of it as just a bunch of same color box. These are same color ball and same color box. So you have these four cases. This is the first thing. What about the second thing? The second thing is how do you throw the ball into the box? So you have freedom, no restriction at all. You can do it, whatever thing you do. That means what? That means this case also include you don't throw the ball. 0. Okay. What about these two? These two is one is on ball and one is on box. So for the 1-1, injective function means you need to throw the ball. So you are looking from the ball perspective. What about surjective? Surjective means you look at from the box perspective. You say that each box needs to have some ball. So from the first case, it said all the ball have to throw away. So it's possible all the ball go to one box, right? And then what about the second case? The second case is all the box has to be filled. So it's possible this guy have a doppelganger or some magic that can distribute itself 4 times to here, right? So these are two very different things. And these have different meaning in the coding. So you need to be aware of this kind of thing. And this table thinking is basically like the following. You have to connect two separate categories of stuff. So you have some stuff here and some stuff here. So each stuff here is some ball. Each stuff here is some box. And then you want to connect them in some way. This is called graph, okay, bipartite graph. But I didn't say you cannot have this, right? You can have one ball go to 2 boxes or even one ball go to all the boxes. It depends on your application. So the first thing to do when you need to deal with this kind of thing, you need to think about which boxes your situation belongs to. So if you have the first case, no restriction, freedom, you can throw whatever way you want, and then all the ball and all the box are different. Then how many ways you can get it? Is Kn. So what does it mean? It means K and then K and then K and then K. Suppose I have 3 balls. I have 4 boxes. So what is the way? How many ways I can put the ball in a box in the first case? I have 4 boxes, right? So this guy have 4 choices. So 4. Then what about the second ball? It also have 4 choices, right? Because 3. So 4 times 4, and then 4 times 4 times 4. It's like this. Okay. Then what about this indistinguishable ball? Distinguishable box. So this box are different box. So that means if I throw a box here, it's not the same as throw a box here. So you can think of this is Joe Biden, this is Mike Tyson or something else. So you fight Joe Biden, it's not the same as fighting Tyson. Something like that, okay? Again, you make your own story. Different people have different story, okay? I always use a boxing story because that's easy for me. Then, how do you do that? What is this? This is n plus k minus 1 choose n, or n plus k minus 1 choose k minus 1. So just a recap. Minus 1 choose k minus 1, and n minus... They are the same. First of all, need to remind you, they are the same. Because a, b, and a minus b are the same thing, okay? This is symmetry of the binomial coefficient. You have n thing, you distribute in n, but you allow duplication in k. And you subtract 1 because whenever you make decision from ball 2 and ball 3, you are referring back to 1, so you subtract 1. This is one way I talk about in the class for the year 2 student, and I also use the star and bar to talk about it. And then because of time, I have only 3 minutes left, so cannot talk about more. Again, I'm saying this half hour is just a hyperbolic time chamber that I can only point where you should look at. It's not, okay, I explained this in half hour, impossible. For example, what is Sn? I didn't talk about what is Stirling number. No time to talk about it, okay? So what is this case? You have to do something called Stirling number. Go to website, Google it, learn it, okay? And then what about this? N partition K. Then what is N partition K? I just talk about it, this spell number. Okay, so that means what? That means this free slide, only 3 pages. But this free slide, the content is 36 hours, something like that. Yeah, there are people spend 36 hours on this. Okay, so don't underestimate it. And then what about this one? Well, now you will see some permutation and combination thing. So basically this one is the most trivial one. It's the permutation and this one is the combination. But again, no time. So let me recap. What is this complete search? Complete search means brute force if you ignore the efficiency. That means first you need to have what? List all the possible cases. If you cannot even list all the possible cases, you cannot even write a for loop or while loop. Okay? Then before this, you need to know what is all possible cases. That means how big is the set. Because before you know the set of all possible cases, you better need to know how big is this set. If this is 7 things, that means you have 7 stuff here. If you know some of them, actually this number tells you what are the remaining stuff. But if you don't even know this stuff, then you cannot even do the yellow thing. So this means what? You need to know how to count stuff. That's why you learn combinatorics. Okay? And then for different problem, you have different interaction between the stuff. You have permutation, okay? Mike Tyson, Joe Biden example. This one, combination. Again, Mike Tyson, Joe Biden example. And again, you also have the case that you allow repetition and not allow repetition, which no time to talk about it. This is actually inside this 12 box, okay, somewhere here. And then apart from this, you have partition and the arrangement. These two are not in here. So that means basically you have 12 possible things plus 2. And if you are very good at knowing this 14, let's say you have a computational problem, you don't know what the heck how to solve it, but if you can identify which case is it, you already have a very good start. So you need to know what is a partition, what is the arrangement. You don't need to know how the heck get this formula. You know this formula enough. Of course, it's better you know why this formula exists. How do you prove this formula? Mathematical induction, okay? And then the arrangement, same. You have this funny factorial thing. This is not factorial, this is opposite. Lastly, you need to know whenever you have two kind of stuff, you need to interact. It's the same as you draw a bunch of lines here. And the line represent they interact. It's like a relation, okay? And then this is like what? This is like how the relation are controlled. No rule, some rule from the input, some rule from the output. You can think of this as input, you can think of this as output, or you can think of this as set A, this is set B, so you draw a line between them. So this is for the line. And what about this? This is on the property of the object. So basically counting is like you have two elements. The object itself, so these are objects, and number 2, how you draw them. And you identify the property of this in your problem, then you just throw in the formula inside, then you have a starting point. And all of them, or many of them, except these two, many of them are exponentially complexity. That means what? That means let's say n and k are 10, okay, immediately you cannot do brute force. And that means what? That means knowing this formula also tells you, let's say, in what cases you can do brute force and what cases you cannot do brute force. Nobody will do a brute force on 10 power 10, right? But if you have 10 2, you can do brute force. 100 is not big. What is big? 1,000 or 1 million. If the problem size over 1 million, forget about brute force. You cannot do brute force. But if it's, let's say, 1,000, you can still do brute force. Depending on how much it takes for one iteration in the brute force. It's possible that one iteration takes 1 hour, then 100 steps a few days, so it's not good. Okay? So that means, let me recap finally. Know this thing, please, and then know this thing, and do revision on this. Then now you basically know everything about this thing. This is just a fancy name. Okay? Done. And this is you, okay?